All right, let's look at this think, pair, share. This one's about laptop batteries. So a computer company that claims its laptop batteries average more than 3.5 hours of use per charge. A sample of 45 batteries um, last on average, last on average 3.72 hours. Assume the population standard deviation is 0.7 hours. Test the company's claim at the significance level of 0.10 by comparing the critical value versus the test statistic and the significance level versus the p-value. All right, so let's dive into this one. So we're going to start with step one, okay, which is going to be to identify our given information. So let's say a computer company claims its laptop batteries average more than 3.5 hours per charge. So we're dealing with a population mean that is greater than 3.5. Okay, and this is our original claim. Okay, a sample of 45 batteries. Okay, so we've got a sample size of 45. Lasts on average 3.72 hours. So our sample mean is 3.72. Assume the population standard deviation is 0.7. So the population standard deviation is 0.7. Test the company's claim at a significance level of 10%, which means we're looking at a confidence level of 90%. Okay. Now, the thing to point out here is that the population standard deviation is known. Okay. We were told what it was. So this is going to imply that we're using a normal distribution. And this is also one with one sample mean. Okay, so let's move on to step two. So step two is to set up our null and alternate hypotheses. So let's put down our original claim first. All right. So I guess we can put down our original claim. We can also make a complement of that if you want to do that right away. And, the null hypothesis is the inequality that actually has an equality in it. So that's going to be this top one because we have less than or equal to. And then the alternate hypothesis is our original claim. Now, the alternate hypothesis will tell us if we're dealing with a left-tailed, right-tailed, or two-tailed distribution. And what we can see here is that if we were to make an arrow out of this, it's pointing to the right. So this is going to be a right-tailed distribution. All right, so now we can move on to step three. And so step three is to calculate the test statistic and the p-value that goes with it. Now the p-value, just because I want to keep it in sync with these, what gives it here? Usually the p-value, we would have to use normal CDF. But yeah, we'll get the p-value after the z-test. So we'll get both. Okay. Um, all right, so let's calculate these. So we're going to be using the z-test function on the Texas Instruments calculator, as well as the NumWorks calculator. So let's see here. Yeah, so z-test, we're going to be dealing with stats. This value, mu naught, that's this value of 3.5. So we'll put 3.5 there. We got a standard deviation of 0.7, sample mean of 3.72 hours with a sample size of 45. And our alternate hypothesis is greater than is greater than 3.5. So it's actually going to be this option on the Texas Instruments calculator. With the NumWorks, this is going to be 3.5 like that. And we're going to have mu greater than 3.5. And then we've got a sample mean of 3.72, standard deviation of 0.7, sample size of 45, and a significance level of 0.10. All right, 10%. Yep. All right, so it'll end up calculating that. So we'll put those values in. So let's go ahead with the Texas Instruments. We want the z-test function. So we're going to hit the stat button, go to tests, and the first one is a z-test. We're going to be inputting stats. So I'll put 3.5 here. Population standard deviation of 0.7. Sample mean of 3.72. Sample size of 45. And our alternate hypothesis is mu greater than 3.5, like that. And then we'll do calculate, but I want to put these values into the NumWorks calculator next. So I'm going to leave that up. We're going to go to the inference because we're doing inferential statistics. That's what a hypothesis test is. It's inferential statistics. Okay, tests. Okay, we're doing a test on a single mean. And it's going to be a z-test because we're dealing with a normal distribution. And the value here is 3.5. And our alternate hypothesis is greater than. Now, notice too that, like I've been teaching you that if the alternate is like mu greater than, then what's the complement? That it's less than or equal to. And it's common, I've noticed to not have the less than and just focus on just the equal to part. So you'll see this in your homework as well. Okay, so if you're doing the alternate hypothesis and you're following my instruction and you said, well, then this should be less than or equal to, this is a common thing that they just kind of do away with the less than or greater than and they just keep the equality. Okay. And we are going to input statistics. So we got a sample mean of 3.72, standard deviation of 0.7, sample size of 45, significance level of 0.1. All right. So we get a test statistic of 2.108 and a p-value of 0.0175. So let's check that here. Yep. So you can see we're getting the exact same values for both. All right. So let's go here, and then just go ahead and write that down. So our test statistic is 2.108, and our p-value is 0.0175. All right, so we use the Texas Instruments to get both of those values, and we use the NumWorks calculator also to get those two values. Okay, so yeah, so that's actually printed down there. So I'll put 2.108 and 0.0175. All right. Now, if we wanted to, if you wanted to calculate this by hand, this is the formula for getting the test statistic. So we'd have 3.72 minus our population mean, 0.7 divided by the square root of 45. When you put that in your calculator and simplify it, then you'll get a test statistic of 2.108. Okay. So this is the equation that the calculator is actually using to get that value. All right, so that's step 3. Let's move on to step 4. Come on, computer. There we go. Yeah, there we go. Okay. So step 4 is to set up the distribution and calculate our critical value. So let's go ahead and draw it. Let's do a quick sketch. All right, and what did I say this was? I think I said that this was a right-tailed, that this will be a right-tailed distribution. So we're going to expect our critical value to be positive, and we have a significance level of 0.10. That's this area here in the tail. Above the tail is where we have the reject the null region. And on the opposite side is the fail to reject the null region. All right. So we have a significance level of 0.10, then we've got a confidence level of 0.90. And we know we got a test statistic of 2.108. So let's actually kind of carry this over from the previous page. 2.108, and we got a p-value of 0.0175. So I'm just carrying this over from the previous page. Okay, so we want to know, where our test statistic's going to be relative to this critical value. So we need to calculate the critical value from this area of significance level. So for that, we'll use inverse norm. And so we're going to have an area of 0.10 with a mean of 0, standard deviation of 1, area to the right. And on the NumWorks calculator, we're going to go using the distributions app, mean of 0, standard deviation of 1, area to the right, with an area of 0.10. And let's take a look at that. That'll give us our Z critical value here at the bottom. So let's quit out of this. And then let's go to the distribution functions. We'll do inverse norm. And we have an area of 0.1, mean of 0, standard deviation of 1, and we'll do it to the right. So, and then we'll hit paste and enter. And we get 1.22. So I'm rounding it at the third decimal place. So, I'm sorry, 1.282. 282. Let's do the same thing here. So let me go back to home, go to distributions, I want to go to normal. Okay, mean of 0, standard deviation of 1. And I want the area to the right with an area of 10%, 1.282. That's good. Okay. So we have a Z critical value of 1.282. So let me come up here and let me put this in a different color. All right, so where is 2.108 going to be relative to 1.282? So if we've got 0 here and 1.2, 1.3 here, then definitely somewhere out here is going to be where our test statistic is at 2.108. It's greater. And so because our test statistic is greater, that's going to point to rejecting the null. And the p-value that we calculated is this little area adjacent to our test statistic. And we calculated that to be 0.0175. And so if you calculate this area relative to that area, you'll notice that the p-value is smaller. All right. Okay, but we're actually kind of done with step 4. Step 4 was just to kind of draw and illustrate all this stuff. Step 5 is to make this determination. And so if p is smaller, then reject the null error. And so if we look at our p-value, that is 0.0175, and then we look at our significance level, we can clearly see that our p-value is less than, it's smaller than our significance level. And that indicates that we are going to reject the null hypothesis. So, here we're comparing oranges to oranges. We're comparing areas. And up here, we compared values on a number line. So values on a number line. So, apples to apples, oranges to oranges. Okay? But either way, it leads you to the same conclusion that we're rejecting the null hypothesis. So we are going to reject the null. And what was our original claim? Original claim was the alternate hypothesis. So the alternate hypothesis was our original claim. So step 6 is, let's see here. So we are rejecting the null, and the alternate was our original claim. So that means this outcome here in our table is what we're going to write for our conclusion. So step 6 is just to conclude. There is sufficient evidence to support the claim that, I'll use a different color, the company's laptop batteries average. Now I'm going to add another word here that I haven't added before. They average significantly more than, more than 3.5 hours per charge. And now we have to put the confidence level. So with a 90% confidence level. I could have said with a 10% significance level, but I'm just switching it over to confidence level just because. Okay. And that is our final conclusion for this hypothesis test. Now, the thing I added in here was the word significantly. So this word significantly is actually a tip-off that we've done a statistical analysis, and the statistics is saying that it's different. Okay, or that that it's different. That the conclusion we came to is correct, right? So this word significantly is kind of like an important word when it comes to statistics. All right, let me know if you have any questions.